speaker will be Federico Parietti from the engineering and mechanical engineering department on MIT. His talk will be independent control of supernumerary robotic limbs for human augmentation.
I'm Federico from the Mechanical Engineering Department in MIT. I work with Professor Osada. And I'm here to talk to you about a completely new kind of wearable robot. So in the first part of the presentation, we will talk about the concept of the robot, and then we'll focus more on the control, which is the theme of this conference, in the second part of the presentation. So let's start with the main novelty of our concept. As you can see, right now, current wearable robots have in common one thing: they follow the structure of the human body. So you have exoskeletons that essentially apply torque to human joints by essentially being parallel to their structure. You have orthoses that do the same, but for rehabilitation issues and on a single joint as opposed to the whole leg. And then you have prostheses that replace a missing limb, but still stick very closely to the natural structure of the human body. So we decided to change this assumption and just attach two completely independent limbs to the human body. Again, the key here, they're independent, and so they can provide the user with new skills that would not be possible with natural limbs. So that was our first idea. The way we realize it, this is the concept. So we call it supernumerary robotic limbs, or SRL, and we explicitly use the term limbs because these are not arms nor legs. They actually can be both. They're in the middle of the human body, and so they can reach both up, down, even below you where you can't reach. Again, the key here is independence, so they can move independently from your natural arms. Each of these limbs has 3 degrees of freedom, 2 rotational ones in the base, and then 1 prismatic one in the leg itself. Of course, this is a concept. We try to realize it in a way that was as lightweight and as small as possible. So here you can see the mechanical design. The robot is worn at the hip, and there are 2 main, let's say, parts or assemblies. A base with the electronics and the rotational actuators, and then a leg that looks more or less like a hiking pole, but it can extend and retract. So the prismatic actuator is included here. The actual prototype looks like this. So as you can see, it's worn through a harness. There is a belt, and the belt is there to withstand to allow you to carry the robot around. And then there are 2 leg straps. We'll consider them a little bit closer later. And they allow you to discharge your weight on the robot. So essentially, we can have this transfer of force between the robot and the human in every direction. These are the 2 rotational degrees of freedom, and then the prismatic joint is inside here. Now, here you see a simple hemispherical foot, but we are actually working on a lot of different passive and effectors at the end. We don't really put robotic hands or active actuators in the end because that would be adding mass very far from the human, and so adding a lot of inertia, and users really hate that. Okay, so I want now to move on into some particular design features of this prototype that allowed us to really cut the weight and also reduce the inertia. So as you can see, the axis, these are the 2 actuators at the base. The axis of these 2 rotational actuators intersect in a single point, and so they form an equivalent ball joint. Actually, to be more accurate, this is a universal joint because it has 2 degrees of freedom, 2 rotational degrees of freedom. Now, the axis of the robotic leg goes to the same point. It's the same here and here. So this means that if we have a linear load, which is actual to this leg, it goes to the center of the ball joint, and it doesn't generate torques on the 2 joints here at the base. So this allows us to pick very small motors here, very small servo actuators, that essentially are there only to move the leg when it's not loaded, or to compensate for disturbances, but they can't really lift you. The lifting part is done entirely by the linear servo. So this allowed us to really reduce the weight. Now, comfort is essential for any wearable robot. Actually, it's one of the, I would say it's the second most important thing after aesthetics. How is our harness, and how is this managed? So here you can see our interface between the robot and a human. So the harness doesn't really get in the way. That was our main goal. So you can move around, no problem. You can jump. You can step sideways. The robot really doesn't limit the motion of the user. Now, how can we sit on the robot? How can the robot actually lift the user and provide support? Because we have these straps on the back. So when you sit down, the straps are essentially below you. It's a little bit like a flexible chair. Moreover, this is essential. The center of mass of the robot is as close as possible to the center of mass of the human and a line below it. This means you don't need any additional torques to compensate for any misalignment. When you're standing, it just discharges through your joint to the bones. It doesn't really fatigue you. Another huge part was making this very light. So it's only around 6 pounds, and it can lift a person at around 200 pounds. The reason we made it like this is that essentially there is no metal inside here, except for some parts in the actuators. It's entirely made of carbon and Kevlar, and later I will tell you how. It's also very, very fast to wear. There are only essentially 3 quick-release buckles. Now, just to give you a comparison with the state-of-the-art in exoskeletons. Each one of these yellow rectangles represents a strap, and these essentially are the market leaders in exoskeleton technology. So obviously an exoskeleton needs to transmit force to every joint. So you need at least one strap above the knee, one below, and one in the ankles, and then any combination of straps here to transmit the load. They even have straps around the shoulders to carry the robot. These robots, in fact, are very heavy, traditional exoskeletons, because they are paired to your muscles, and so they need to try to be as good as muscles, right? Because otherwise they will get in the way of any motion, residual motion the user might have. We don't have any of these constraints. We don't need to be as good as muscles. We're independent, right? So we don't get in the way. We don't really need to actuate the human knee, so we can just have these simple 3 straps, and that's it. So this is actually a robot that a patient would be able to wear alone at home without any particular assistance. Also, state-of-the-art exoskeletons usually weight in the ballpark of 50 pounds, and we are around 6. Now, this is the key concept for us, is assisting without getting in the way. Now, you can see a user wearing the robot. And so the legs of the user are free to move. The arms of the user are free to manipulate an object. And the robot can still provide weight support in this case. Now, I mentioned before that the entire robot is made of carbon fiber and Kevlar. We can do this because there is a pretty cool startup out of MIT. We're not associated with them, but we work with them because they really want to get some cool use case. And so essentially they can embed carbon fiber or Kevlar fibers inside a normal 3D printed nylon part. So we can have the same weight as a normal plastic part, but it's as strong as aluminum. So this was really a game changer for us. Now that we consider the structure of the robot, I'd like to outline some of the possible applications for this kind of technology. These, of course, are very nice questions. Once you have additional arms or legs, what do you do with them? So here are some of the applications. We considered manufacturing. So our first sponsor for this project was Boeing. So in particular, heavy manufacturing, aircraft, shipbuilding. Construction is also a very important field, both because it's very heavy and fatiguing, and because there are a lot of safety issues. And now recently we're also starting to work on rehabilitation and elderly assistance. And we are about to start testing in a rehabilitation hospital nearby. So we're very excited about that. Okay, so now that you know what the robot is about, it's time to think about the most important challenge, which was not the design. So design was hard, but it was not the challenge. The challenge here is how do you make it useful? For what should the robot do? And the second challenge is how should the robot know what the user wanted to do? What is this interface, this control between the user and the robot? How can we make it seamless and natural? So let's start with the simplest possible application, static case. We just want to compensate for the weight of the human. And we could do that being essentially like a chair, so sitting on the floor, just pushing down. Or we could use the very wide workspace of the robot and just grab anywhere else onto any, say, structure that gives us a essentially a grasping surface. This would not be practical in a house, but it was very practical inside an aircraft because there are beams everywhere, and so this was for assisting the workers. We call this the bracing strategy because the human is supported by the robot, is braced by the robot that pushes on the ground to provide the support. So this is the framework of the problem. We want to support the weight, compensate for the weight of the human. We want to minimize the human workload, so essentially the torque or forces that the human needs to exert in order to compensate for his or her own weight. And we want to do so without exceeding the maximum forces of the robot. We're not really particularly limited in this direction, but obviously the torques here are very limited. And then we want to do this with taking essentially as an input the position of the human, so the human is free to decide where to be, and taking also as an input the available contact points with the environment. So this is an optimization. We have here an example cost function. You can see that the minimum cost is like we expected, either on the roof or on the floor. So you either push down or hang from the ceiling. Now, this only tells us a static equilibrium configuration that we can achieve, but doesn't tell us anything about stability. So is it stable? We can calculate the stiffness matrix, this Kp here, around the hip of the robot or of the human, because they are linked. And of course, if the eigenvalues of these matrix are positive, then the system is stable. Now, here you can see a simple 2D case. And you can see if we hang from the ceiling, so the hands of the robot are like this, the system is stable because it's like a pendulum, right? While if this angle increases over 90 degrees here, we go into an unstable region, it's like a pendulum, right? Now, how can we stabilize this system? There are two ways. One is very easy, right? Just change the gains in the robot joints, try to make it stiffer, right? But there is a smarter way, and even simpler, which is this is a closed kinematic chain. So essentially, the robot has 2 points of contact with the ground. So it can generate internal torques that don't really generate any motion. It just increases the internal torques. All right? These are torques that belong to the so-called null space of the robot. Now, these torques, turns out, influence the equivalent stiffness at the hip of the robot, and they are multiplied by the Hessian matrices. So using these torques, and when we really need it by tweaking the P gain, we can stabilize the robot in any situation. The only constraint here is actually the actual actuator torques of the robot. Here you can see a small example of this. Here we are. Okay. So this is the case use of a worker in an aircraft manufacturing. If you want to work in a very uncomfortable position, the robot just supports your weight, and then you slide. Now, this is very static or quasi-static, but how can we use these extra legs to help the user in a dynamic situation, like, for example, walking? Our approach here is the following. We increase the support polygon of the user. The support polygon is this area here that you see shaded. And essentially, let's say in the static case, if the projection of your center of mass lies in this area, then essentially you don't fall down. If someone pushes you and the center of mass is on the side, then you fall down, right? So if you could have a giant support polygon, you would be like a table or a car, right? So you need to push a lot before actually starting to flip. Now, this is a static concept. You could use something like a ZMP, and that would be dynamic. You could extend it to dynamic, and that's actually how the Japanese walkers, Japanese humanoids walk. But we were just interested to try this technology, so this idea, and so we tried out just using the support polygon. How do we integrate with the gait of the user? And we had to come up with new gaits. New gaits, for example, in this case, the robot touches, so let's say your right leg is touching the ground because you're stepping. Then the left leg of the robot touches the ground at the same time and then follows it. and the same with the left human leg and right robot leg, right? So we are essentially developing gates that coordinate with the user and maximize the support polygon. Now, a lot of people ask me, how does it compare to quadrupeds or horses? And my answer is very different because there is a hierarchy between the legs. So horses or animals usually can rely on all of their legs and control them at the same time. In this case, there are two leader legs, the human legs, that can do whatever they want. And the scope of the robot, the purpose of this robot is to provide as much assistance as possible, following them, though, without really relying on them to do anything. So this is why we have so much freedom in determining our gates. So this gate here in particular maximized the instantaneous support polygon. So here you can see when all the 4 legs are on the ground, it's huge. But then at some point, you only have 2 on the ground. We can even, if we want to optimize something else, for example, optimize the average area of the support polygon. So in this case, you have always 3 legs on the ground. We are not constrained by anything. We can really do whatever we want in this case. And we could pick any cost function, any target, and the robot then would use that to optimize the gate. An interesting thing here is how do we tell the robot that the human is walking, how fast it's walking? Well, luckily, walking is a well-understood periodic activity. And so for us, it worked very well to have this simple solution. We had an accelerometer here in IMU. We detect the impacts, so every step with the ground. I know my height. There are a lot of, in the literature, a lot of relationships between leg length, stepping frequency, and, for example, step length. So the robot knows pretty much what I'm doing, assuming that I'm an healthy individual. And so it just coordinates with my speed. Of course, this doesn't integrate turning yet, but it works pretty well on a treadmill. Now, here there is an example of this application. And now you see that the huge problem for us, this was the old prototype, was the contact with the ground. We can't really guarantee much contact because we were using these electric actuators that are very stiff. Here I tried to compensate for this problem by adding a spring damper. It was a very bad idea because I was adding mass right at the end of the leg. The new carbon leg is much lighter, and everything, all the mass is here, so the rest is essentially an empty carbon tube. So we are just about to test the same algorithm with the new super light robot. But again, walking is periodic, so it doesn't really come close to what this robot can actually do, which is giving you 2 additional arms, right? So if you have 2 additional arms, let's say you are in aircraft manufacturing. Like you want to do a very complicated task using 4 arms. Let's say that the robot wants to grasp the structure to give you safety, and then support your drill bit in a particular location. Now, we did this demo for Boeing a couple of years ago, and since they sent us a lot of managers, they didn't really understand what was going on, so we kind of tricked them, but it was this was cheating, right? Because I was using a simple app on a tablet on my forearm, so I was using my arms to tell the extra arms what to do, which completely misses the point. But this is hard, right? Because there's not really a periodic way to coordinate with me. You can't really, and you can't hard code it because it was just impossible to cover all the variability inside the aircraft. You could try to learn by demonstration, but that would require a very long training and a lot of data. So the solution is how can we have a direct link between the mind, if you will, or the neural signals of the user and the robot itself. So to answer this question, we had a simulation first, but then also the real robot, so don't worry. There will be more videos. This is the robot. This is simulation. We just took away the human from the simulation, not to get in the way. And we took only 2 degrees of freedom, so each of these arms can rotate back and forth. Okay. Each one of the robotic arms has a target. The 2 targets move completely randomly. They hold a position for 15 seconds, and then they move to the next target independently. And the goal of the robot is, of course, to track these targets with the end effector. Now, what are the signals that we can use to let the humans control these arms? So we need signals, to recap, we need signals that are independent from the motion of the limbs, that in general don't require any motion from the human, and that are simple and non-invasive to measure. So a lot of the suggestions that we get are like, okay, just use an electrode array on the brain, right? But no, healthy person would ever accept that, right? So we need to be very non-invasive. So the solution we went for is to use the muscles in the torso. So we can use these electromyographic EMG signals, the same that you have seen in the previous presentation. But we don't use the muscles of the arms to control the arms. We use completely unrelated muscles to control the arms, right? And this is very interesting because we have so many muscles and degrees of freedom in the torso that you can contract them. There are some combination of contractions that we can generate without moving. So for example, if you try, you just contract your muscles, you're not moving any of your limbs, right? That's called the null space of your torso, right? So we are using those signals to control the extra arms without really stopping or being an obstacle to your natural arms. So this is how it works. We wire people up with this sensor suit. We measure the pectoral and the abdominal muscles for no particular reason, just they are the easiest to access. And then the user has a target, here a simulated robot on the screen, and they need to track these two targets. Now, what is the association between muscles and motions? Essentially, we use the pectoral muscles to move the leg up and the abdominals to move it down. This is arbitrary. I acknowledge that, but we try to have an arbitrary connection that's as natural as possible. So, for example, we have antagonistic couple of muscles. So your pectoral and your abdominal on the same side are on the same joint, exactly like your biceps and triceps. There is the same lateralization, so your right side controls the right of the robot, the left of the robot. And then, intuitively, you use the pecs to raise and the abs to lower. Okay? So that's the association that says signal to degree of freedom. What is the control law that links the EMG signal to the actual motion of the user? We tested three control laws, position control, velocity, and let's say a muscle model. Here the only thing to keep in mind is that, for example, in position control, the EMG signal becomes a position reference. So if you want to hold, for example, maximum position, you need to hold maximum contraction. As soon as you relax, it goes down, right? So zero contraction, zero position. The same with velocity and muscle model. Let's not forget the actual natural limbs of the user. The users were standing, so they can't really use their legs, because they're using them to stand. And their hands were grasping joysticks. I was making sure that they were actually holding a trigger. And I told them not to move them because I was measuring them. So it was actually, they could not use really their arms to kind of cheat and generate the EMG signals. It was only torso. So here, I can show you some results about this. So first there is a simulation. So here you see subjects tracking the targets. But then, I just pick the best control strategy. You see later what it is, and put it on the rear robot. And actually, by chance, one of my subjects went, now you can see, to the same university and was wearing that T-shirt. So it's a lucky coincidence. So as you can see, people can really track the targets really well. It's very natural. They learn within 60 seconds. I thought the task was too hard because the two targets are completely independent. But actually, yeah, they were bored by the end. This is an example of tracking. So they converge to this point within 10 minutes. They track the trajectory very well. They essentially don't move the joystick here. And they just use the muscles when they need it. And they adapt so well that I didn't even need to filter the heart. So this is not noise, this is the heartbeat. I didn't even need to filter the heartbeat. They just compensate for it in 60 seconds. Like the human brain is really amazing. So this is an example with velocity control. As you can see, this is the tracking error for velocity control. Here, velocity is by far the lowest. People find it very comfortable because they just need a small blip, and then you have a discrete, steady state change in the position of the arm. You don't need to hold the contraction. Velocity control also has the minimum effort, so minimum EMG average, and the minimum motion of the joystick, so let's say maximum independence. This is just a quick result. People just learned very well and improved on the second day with every possible technique. So they were even doing better in the other control strategies. And then they, of course, learned very well to control the robot itself, which was very interesting. Actually, controlling the robot was better than controlling the simulation. We don't really know why. We think it's because of the haptic feedback. It was interesting because sometimes, for example, one of the subjects hit something with the extra leg, and immediately froze. It's like, I'm touching something, like, what's happening? So, like, within 2 minutes, he integrated the extra limbs into his perception of his own body. So our preliminary answer is that, yes, it's possible to have additional arms, and your brain is pretty okay with it. So right now, we only have 1 degree of freedom per arm, and so the future would be, what about adding more degree of freedom, right? So we can actually do complex tasks. So with this, it's the end, and I'm happy to take any questions.
Let's have one quick question.
So you're using all those EMUs on the torso to make the movements, right? So when you do a complex task like showing this instruction on going plane, aren't you going to what are the involuntary contractile abdominal muscles? How do you differentiate between torso and
Yeah, so there's going to be a lot of probably machine learning applications to that. But the idea is that what's striking about the torso is that we have a lot of muscles and a lot of degree of freedom that we don't really use in these tasks, right? So the idea, what we want to study actually next is how can we exploit these co-coordinations, the co-contractions, right, that you can actually use and just isolate that signals for an independent motion, right? And probably the limit that we have is more than the brain or your ability to learn. The limit is going to be how many sensors we can actually fit comfortably on your torso. Because really, like for us, the main issues here was essentially signal quality. If you get the EMG right, you must learn in 60 seconds.